Are we ready again? So, some of you guys came down to me and said, Mads, you just said that we can't move T from the right-hand side to the left-hand side without removing a star. And then you said, Mads, are you crazy? Because of course we can do that. And yes, that is true. I said it on purpose because we can only do that after we know this. So let's just do that calculation. So we know that if we have our let's say V and then T, W, where again T is a linear and bounded operator, then by this, and only after we've shown this, we can do the following. We know that this is the same as V inner product with T star W. And then of course, what I said earlier is still correct here, that we can move an operator from the right-hand side to the left-hand side if we remove a star. So then we get just T star V W. Okay? So with this knowledge, then you may do this, have an operator on the right-hand side and move it on the left-hand side with a star. Which is exactly the same up here, just in reverse. And we can do this just because we know this. Okay? So until you've proven this in the exercise today, you may not do this. Okay. And yes. So now we continue with some special operators. So this is actually a definition. 4, 5, 4. So if we have an operator T which goes from a Hilbert space into a Hilbert space, which is linear and bounded, of course it is, otherwise we can't do anything, which is then some special things can happen. And for instance, if you take the adjoint of the adjoint, and now here T really goes from H to H, okay? So in the definition we said, we can also do the same if we have a T that goes from K to H, and then the adjoint will go from H to K. But here we really need from H to H, okay? So this is not a simplification because I don't want to talk too much. This is really just as it has to be. And then we say that T is self-adjoint. Well, who had guessed it? If T equals T star. So this is, well, if really T is equal to T star, then we call it self-adjoint. So this is a special kind of operator. And what else? Well, we also say T is unitary. If what is it? T star is the same as T star T, which is the identity operator. So, you know, in mathematics 4, we stop to think about finite dimensional Hilbert spaces, meaning Rn or Cn, which we do in mathematics 1, where we have this concept of orthogonality, which we already have generalized by the inner product. And these operators here, they are also just special names for operators we already know from our mathematics 1 class, where we talk about operators going from Rn to Rn, meaning matrices. So let's just write this as well. So for the special case, where H is Rn, we'll put in parentheses as well Cn, because both are finite dimensional Hilbert spaces. Then the word self-adjoint means, or is the same as a symmetric matrix. And the word unitary means orthogonal. So in finite dimensional spaces, Rn or Cn, all linear maps can be written as matrices. So no matter which case of Rn, R1, 2, 3, or so on, or C, 1, 2, 3, you consider, then all linear maps, meaning all operators we can do this with, doing the adjoint, make the adjoint, that these operators are also bounded, and we call operators satisfying this symmetric, and operators satisfying this orthogonal. And when we go from finite dimensions to infinite dimensions, like in the case of little L2 on the natural line, or I think next week we will also see capital L2 of the real line, then we don't use the word symmetric or orthogonal anymore, but use the words self-adjoint and unitary. Why is it at all interesting to look at infinite dimensions? Because the real world is infinite dimensional. When you look at partial differential equations, you will usually look at solutions in capital L2 of Rn, just like physicists look at that Hilbert space when they do quantum mechanics, and or some other kinds of Hilbert spaces. And they will also be infinite dimensional. But the problem is when we want to solve some equations or do some simulations on computers, the only thing we can do on computers is not infinite dimensional. It can only be finite dimensional, because you can't store an infinite number of numbers in a computer. So what you do is you go from finite dimensions to infinite dimensions, and this process is very tricky. And some concepts, they can be generalized from finite dimensions to infinite dimensions without a problem, just like we see here. So instead of symmetric, we say, it's self-adjoint. Instead of orthogonal, it's unitary. And then when you do simulations, numerical simulations, the interesting thing is, okay, so if I now approximate my real-life infinite dimensional problem with finite dimensions, will my solutions, which always are finite dimensional, approximate the real thing I want to? And that's a question which is based on what we do here, and also another class which is called functional analysis. The question of convergence. Okay, that's just a side note. Forget it if you don't like it. Okay, so that was symmetric and orthogonal. Now, do we have a symmetric or orthogonal operator? Well, of course we do, because we can simply say symmetric or orthogonal operators, matrices, but they are boring because they're just finite dimensions. So we had this example before, which I wiped away again, but we still have the definition of the operator here, which is this one. So we saw that the operator, this T up there, which will appear in just a minute, has the adjoint we calculated a little while ago. So I will just write it again here. So we have T applied to some sequence xk, and xk is in little L2 indexed by the natural numbers. Then we know that this, well, per definition, is x1 plus x2, x2 plus x3, x3 plus x4, and so on. And we know by previous calculations that the adjoint applied to a sequence is, let's just call that y again. So yk, then we get y1 plus y2, y2 plus y3, and so on. So just from this definition we see, well, T is not equal to T star at all, because it's not the same, especially not in the first entry. Therefore, this operator T is not self-adjoint, because we don't have this equality. What about unitary? Well, let's do a calculation. We can just write, so T is not self-adjoint. That is, T is not equal to T star. what about unitary? Well, to be unitary, we need this equality, or both equalities. Okay? Note, just because this is satisfied doesn't mean this is satisfied. We have to check both. And of course, if one goes wrong, then we don't need to check the other one. So let's look at T applied to T star, which takes a vector y1, y2, and so on. Well, this is T applied to what we have here. So let's say y1 plus y2, y2 plus y3, and so on. Okay, so what does T do? Well, T takes the first element and the second element in the first entry. So we have down here, can you still see? Otherwise, I do like this. So y1 plus y2, and on the second entry we get x2 plus x3, so that would be this plus this. So we get y1 plus y2 plus y2 plus y3, and then we get y2 plus y3 plus y3 plus y4, and so on. And this is not the identity operator. So this operator T here is quite boring because it's neither self-adjoint nor unitary. Okay. Then there's also another example. Yeah?
Do you use also the word inverse for something, well, for operators and for never?
The inverse. Yeah, okay, so if this is satisfied, then of course T star is the same as the inverse. Yeah, that's true. That's something that follows from the definition of the unitary operators. Does that answer your question? Yeah. Okay.
No, it's orthogonal, also inverse.
That's a good question. So just because, okay. So we say an operator is unitary if this is satisfied. By definition, so we repeat the definition of inverse operator. Inverse of T needs to satisfy. So we say S is the inverse of T if this is satisfied. Ts equal to Ts equal to the identity operator. So simply because of the definition of the inverse operator, if we have a unitary operator, then naturally T star, since it satisfies this equation, is S and thereby the inverse of T. Okay? And of course, if... Yeah, okay, I will stop here. Yes. Okay. Yeah? Okay, so the other example is somewhere here, and it is concerned with matrices. Since we also talked about matrices over there, we'll also have an example of this, and this is an example you will actually calculate yourself today. So this is exercise 419. And, well, it says if we consider a linear map. Let's call it A. That goes from Cn into Cn. Linear maps from finite dimensional Hilbert spaces to finite dimensional Hilbert spaces are always bounded. So we don't need to talk about that. And we define that the usual way. So another thing, if we have a linear map from Cn to Cn, then we can always write that as a matrix. Hence, if we have A applied to a vector x, let's put a bar on it, then this shall be written like this, A11, A12, and so on to A1n, and here A21, A31, etc. And down here we have A and n. So this is simply a matrix times the vector x1, x2 to xn. Then the adjoint, and that's what you will show. The adjoint is given by, so the adjoint of A is A star, which is the following. So we have A11, and then we get A21 here. So we transpose the matrix. A31 on here we have A12, A13, etc. And A and N down here. And all of them complex conjugated. And this we recognize we can also write another way, namely as the transpose of the matrix, which is complex conjugated. If you first complex conjugate and transpose, or first transpose and complex conjugate is up to you, it's the same. And this will be the adjoint of A. Again, for physicists in this class, the adjoint as such is not so interesting, but only if the operator, in quantum mechanics you look at linear operators, and if this is self-adjoint, then you are really interested in it, because all the observables in quantum mechanics, they are given by self-adjoint linear operators. And since you also use matrices in quantum mechanics, this as well is very interesting for you. Okay. So this we show in an exercise today. And now we continue with something completely else. So is there anything left to say about this? So what have we done? We had a linear unbounded operator T, which goes from a Hilbert space to a Hilbert space. They not need to be the same. Then we can define the adjoint operator so that 413 is satisfied, meaning that we can, if we have the operator in the left entry, we can move it to the right entry and back again if we want to. If T is the same as T star, it's self-adjoint. If this is satisfied, it's unitary. And we've seen examples. We have calculated the adjoint. How do we do that? Well, the only thing we can do is take the definition and see, well, on the left-hand side, we have T applied to some vector, inner product with some other vector. Then we look at the inner product and somehow try to isolate the left-hand vector, which is called V up here, in the inner product, so that we see whatever remains on the right-hand side of the entry will be the adjoint acting on the other vector W. Are there any questions about that? Yeah?
When does the inverse exist?
So the inverse operator, not always. The left and right shift operators, they are special because one is the inverse of the other, and the other one is not the inverse of the other. So if you have the left and right shift operator, then I don't know which way it has to be turned, but either is this not satisfied or this is not satisfied. Okay. So for the left shift operator, this is not truly true. For finite dimensional matrices, which are regular n times n matrices, then the inverse always exists. But not if we talk about infinite dimensional spaces like here, then this is not, you can't say that beforehand. You always have to check, and check both ways, okay? Because one can be true, but the other one need not be true. Yeah, okay, I was a bit sloppy, I am sorry. So, inverse of T, so let's say the inverse S, the inverse operator S of an operator T satisfies this, okay? Huh? Oh, this is also wrong. So ST, of course. Yes, thank you very much. Was this written there all along? Yeah. What the hell? Okay. Okay, so enough about that. Let's switch topic. We can keep that for amusement. So another important topic in mathematics and vector spaces are bases. So bases, B-A-S-I-S, they are something which is somehow wiped under the carpet in mathematics 1, I think, because we never really, or maybe it is not, well, I think many people don't really know what it is. So let's just do that. So recall, or get to know now, so that V be a finite dimensional and now this doesn't need to be Hilbert spaces anymore. So let's just say finite dimensional vector spaces. So I have Ole's notes here, and it doesn't say normed. So you can also do this on vector spaces. Yes, since it's finite, then there's no problem. So finite dimensional vector spaces. And then a collection of vectors Vk, and k goes now from 1 to capital N, where n is the dimension of this finite dimensional vector space. So a collection of vectors in V, so these are all vectors inside our vector space V. So I just put the bars here to distinguish them from my small v's. If they're for each vector, okay, let's also call this V in V. So we have capital V, which is a space, small v, which is a specific vector, and then we have our VKs. There exists a unique sequence Ck, and how many of those? Well, k from 1 to n, where all Ck are complex numbers if we are in a complex space, such that the following is satisfied, namely that we can write V, so let's try to make this V again here, equal to k from 1 to n over Ck Vk. So this, if this is satisfied, if there is a sequence Vk in a finite dimensional vector space, and there's a unique sequence of coefficients for that, so that no matter which V we take, then we can write this in this way, and this should hold for all V in our space V. Do you know an example of that? If you think of R2 or R3. Now all hands should be up. Yes?
The orthonormal basis.
Yeah, exactly.
What?
What?
Standard E-base.
Yeah, exactly. Yeah, so the standard E-base, apparently what we say in mathematics 1, and that is the nicest basis, or probably also the most understandable basis there is. So, yeah, example. So let's just stay in Rn or Cn. So the vectors v1, which is 1 on the first entry and 0, 0, down to the nth place where we also 0. Then v2 we get 0, 1, 0, and so on. And vn is then 0, 0, and 1 on the last entry. Okay. This is the basis for Cn. So why is that true? Well, for this to be true, we need above definition to be true or satisfied. So what does it mean to be a basis? Well, it means that no matter which vector we take, I will take my favorite vector, 1, 2, 3, 4, 5, up to n. Then no matter which one I take, there's only one way of choosing the sequence of ck's such that I can write my vector like this. When looking at this example here, I hope you believe me that, well, we better choose it in only one way, namely if I have my vector v star, this is called 7, 3, and so on. Well, I need a 7 here, and the only way I can get a 7 is by choosing the coefficient in front of my v1 to be 7. The only way I can get my 3 here is by choosing the coefficient for my second vector with a 3. No matter which one I take, from the other vectors, I will never get anything because they're always 0, except for the nth entry. Okay, so clearly, there's only one way to choose my sequence ck. This definition holds in finite dimensional vector spaces. And yeah, so you called it the standard orthogonal basis, didn't you? And that's because we can consider this in inner product spaces, namely Hilbert spaces. So Cn is the inner product space, and if we take the inner product between any of those, we get 0, and we get 1 if and only if we take the same vector with the same vector. These are some special bases, and we will also consider those later in the classes. But not today, but maybe next time or next time again. But they are very important because they have nice quantities, or properties, it's called. Okay. So that was in finite dimensions. Let us now take... Actually, yeah. So let's be more precise when saying that there's only one way. Yeah. So say now we have found these 1 ck's as I just said, namely that if we want my 7, we take a 7 here and so on. So we call that sequence ck. So let ck be the sequence that is chosen in the obvious way. And now because I have the lecture today, I have the freedom to say obvious. In the homework, you never have the freedom to say obvious, and you never have the freedom to say, of course it's true. You always have to show it. So what's the obvious way? Obvious way, it's a difficult word. Then, of course, we take 7 and 3 and so on. And if that is true, then for all choices, let's call them dk, where dk is different from my chosen sequence ck. I am running out of space. Yeah. Let's do it here. So if I choose my sequence in another way, well then of course my vector I get is also different. And I just want to write that down. So if I have any choice dk which is different from my ck, then my chosen vector v is not equal to the sum over dk vk. Okay, this is simply to be more precise with what I said before. Are there questions, since you're all mumbling? You too? Okay. Can V be a collection of vectors in V is...
I think there should be, after this big V, it should be is a vector.
That is true. So is a basis Yep, thank you. If there for each exists unique. Yes, exactly. Okay. So for finite dimensions, we know everything because we can do matrices and stuff. So what about infinite dimensions? Well, for infinite dimensions, the definition is more or less the same. Well, it's not exactly the same. So definition that is 2, 5, 4. So a sequence. Now we are in infinite dimensions, so we take vk where k goes from 1 to infinity. And now it needs to be a norm vector space, okay? We really need a norm, and you will see why in a minute, in a normed vector space. Sequence in a norm vector space is called a basis. And depending on which literature you see, it will be called a Schauder basis, okay? This is a word we do not put emphasis on in this lecture here, or in this class. But if you read somewhere Schauder basis, then it will be the following. So basis if for each we take again a vector v in our space V. There exists we again need a sequence, we could call it ck from 1 to infinity, where all ck again are complex numbers, such that, well, what do we need? We need, of course, something which reminds of this, but now instead of finite sum, we have an infinite sum. And here comes the dilemma. Because finite sums is no problem in a vector space because vector spaces are closed under addition, right? So if we take an element in a vector space, multiply it with something, and then add another vector to it, we will still be in the space. If you do that n times, there's no problem at all. Over here, we will do that an infinite amount of times. So we can't just write infinity here, because to take an infinite sum, what does that mean? The meaning of this is given by the fact that we are in a normed vector space, because we write this infinity above if we can ensure that this sequence converges. Okay? So whenever you or I or Ole writes this, or someone else, then we can only make sense of the infinity if we have a norm. Because writing infinity means, so let's call this star. That means that V minus the infinite sum, or the finite sum from k equal 1 to capital N, or ck, vk, in the norm of our vector space goes to 0 for n going to infinity. Okay? So whenever we write this, means exactly this. Nothing else. So if there is no sequence, no element to which the sequence converges, then we cannot write this. But as soon as we say that there should be a sequence ck such that this equals to this with an infinite sum, then it means exactly this, that this difference in the norm should go to 0. That is why we need the norm. If we do not have the norm, we have a problem defining convergence. And we have a problem defining infinite series. Actually, this is nothing but the definition of convergence as norm vector spaces, and that is 251 if you want to read that. Okay, so we still have half an hour. That is nice. So what we want to do now is, of course, make an example similar to this. By the way, there's also another delicate question when we look at these infinite series, because this says here that there needs to be an element to which we converge in the space. That is not true necessarily in norm vector spaces, but if we consider Banach spaces, where convergence is the same as being Cauchy and vice versa, we have no problem. So in Banach spaces, finding such a V is no problem because we know it exists. Okay, existence is no problem, but finding it, can also be difficult. Okay, so example. Let us consider a Banach space. We already know some. And the one we want to look at is little L1 on n. So just to remind how that's defined as all sequences xk where all the xk, they are complex numbers, and the sum from k equal to 1 to infinity. Now we have infinity here again. Absolute value xk should be convergent. Now, the same as I said over there can be applied here. So again, when we write 1 to infinity, this means that this sum here converges, meaning it converges in the real numbers where we have a norm, so definition of this infinite series is no problem. We have the class mathematics 2, so I hope you all took that one. So that should not be so new to you. Okay. So, and what we want to do now is we will show that Vk so we want to have a basis for L1 and what is all the VKs? Well, for L1 where so V1 is 1, 0, 0, and so on. V2 is 0, 1, 0, 0, and so on. And V3 is 0, 0, 1, and so on. I guess you can guess the other ones. And yeah, so we want to show that all these VKs, they are a basis where they look like this. Yes, so this is a basis for, I've already written that. Yeah, okay, so what does that mean? That is, we will show that, and this is just by definition of our basis in infinite dimensions, that for any v in little L1 n, can we call it something else than v? Let's call it u. So there exists unique coefficients ck in the complex numbers such that, okay, I'm just writing the definition of the basis actually, u equals to infinite sum from k equal to 1 to infinity over ck vk. Now, in writing this, of course, what I mean is the definition over here, right? So what we have to check for this equality, which is the same as this one, is actually this. So let's do this. So what do we have to show? We have to show that we can only choose these ck in one and only one way. Of course, we could say the same as here. Well, this is obvious, because if we need, you see here, if we take any sequence u where we have some element, let's say 7 again here, so let's take u equal to 7, 3, and so on. Then, well, of course we have to choose this to be 7. And of course we have to choose the coefficient for this vector to be 3, and so on. So it's clear that there should only be one way of choosing the coefficients, but we still have to be a little bit more precise when doing the proof, because we have to consider the definition of the convergence via this finite sum. Okay, so for any n in the natural numbers, and this n will actually be, well, the index on the finite sum over there, and any choice of ck, well, I simply calculate what is the difference between u, where u is my vector I've taken. Then we have our finite sum, because that's what we have to consider, because now we have to show that this norm here goes to 0 if and only if we take our ck's in the obvious way. Okay. So what is this? Well, this is nothing but the following. So we take the norm, and here I will again write my infinite vector like this, just when we did the calculation for the adjoint operator. So we have here u1, u2, u3, un, and so on, minus. Now, this u here is simply the u I've taken, okay? So this will have some coefficients, because otherwise it wouldn't be a sequence in my space. But now here I've chosen my ck's somehow, and I only have c1, c2, up to cn, and then I only get zeros left. I only have zeros left because I only take this finite sum here, okay? So this u is this vector, and this finite sum here gives me this vector. Okay, well, let's use our definition of our minus. So we can simply say, well, this is nothing but u1 minus c1, u2 minus c2, un minus cn, and then we have un plus 1, un plus 2, and so on left, okay? Because we don't have any cn anymore on the right-hand side. So what is the norm? Well, the norm we are looking at is the norm in L1. I don't need to write those, but I just want to emphasize that it is this norm we look into. If you take any other space, if we consider a basis in L2, L3, L4, Cn, then you can't take this norm, because you have to take the norm of the space we're in. Okay. So what is the norm? Well, do we have it somewhere? Oh yes, more or less the expression up there. This one. So what do we get? Well, of course we get an infinite sum, but let's write the first n entries first, because they look similar. So from k equal to 1 up to n, we have u1 minus, uk minus ck in the absolute value. This is some finite sum, so that's no problems at all. Plus, and what do we have left? Well, we have all our uns. So plus k equal to n plus 1 to infinity of, well, only our u case. So when we look at this, what do we need? We want, where do we have it? We want the norm difference to go to 0, right? So this expression here, which we have evaluated now, needs to go to 0. Yeah? All the v's. Or the vk's, you mean? Yeah. Ah, okay. So let's do this down here. I think you will see it as soon as I write it. So if we consider this sum, so what does it say here? It says C1 times V1 plus C2 times V2 plus C3 times V3 and so on. But V1 is this. So okay, so maybe I should be consistent. Here I wrote my vectors as columns and over there as rows, but I will write them as columns here. So here I have 1, 0, 0, 0, and so on. And my V2 will be 0, 1, 0, 0, and so on. So when I add those n vectors here, this is a vector, as is this. These are vectors in little l1, meaning they are sequences. This is a complex number, which I just multiply on top. And then I add these finite vectors here. So I get C1 on the first place plus, well, C2 here. So I get C1, C2 up to Cn and then zeros remaining. Okay, so that was this. And yeah, so what do we want? As I said, we want this to go to 0 because this is the same as this. And by definition of by the definition of basis, we need this to go to 0. So here we have a finite sum over absolute values. They are 0 only in one case, namely if ck is equal to uk. So let's write this here. Thus, if we want we can call this star star. So if we want this expression, star star, to go to 0, the only possible choice is the one we expect, namely ck equal to uk. Because if we do that, then if we make that choice, then this here is 0, and the only thing that is left is this infinite sum. But this is an infinite sum over the UKs, right? And the UK, that is the tail of an infinite series of an element in L1, right? So these UKs, they are the values of our vector u, which lies in L1. So it satisfies this. So this is a convergence sequence. And by mathematics 2, this here will go to 0 because UK lies in L1, because it's in a convergence sequence. So, and since U lies in L1, this here I hope I don't write too small now. This goes to 0. It can't do anything else because it is a convergence sequence. So if we took any other choice of ck's, then this would not go to 0. We can only take the choice ck equal to uk for all k's. There are. And just to finish, yeah?
How can you say that the scalar uk is equal to the vector? No, the opposite. The scalar ck is equal to the vector uk. I know that it only contains one element, but
no. So ck, that's my that's a complex number. For each k, this is a complex number, and uk, that is. So what is uk? uk is what I have in my entries of my vector u. So all the entries in a vector u of L1, they are also complex numbers. So each u1 is one of these. So I can say they are equal. Okay. And now, we simply finish the proof by stating what we are proving. And then we're also done for today. So this shows that u is the same as, and now we have the permission to put this infinity here, because we know that the sequence converges. ck vk with a unique choice of ck's. Thus, vk, meaning the ones written down here, these guys here, they actually form a basis. For L1. Okay. Usually when proving something like this, you first show existence and then uniqueness. And here we did the other way around. We said, well, by definition, we want this to be true. By definition of infinite sum over here, we need this, which is the same as this, needs to go to 0. This can only go to 0 if we choose our ck's equal to uk. And then this automatically goes to 0 because our vector u was in little l1, and hence this here is a convergence sequence. And thereby, we simply said, okay, let's assume we have one. And after that, we show it's unique. Yeah, and as I said, usually we prove it the other way around. We say there exists one sequence, and then it's unique afterwards. But this was merely a trick, because it's nice to use tricks, because otherwise it's a bit difficult to do that. I think there's also an exercise where you have to prove that this actually is the basis for LP. And to do that for LP, you actually do exactly the same. Yeah, okay. So, any questions? Okay, well then, thank you for your attention. See you at the exercise.